All right, what's going on, class? So let's take a look at a few examples involving a series, parallel, combination of resistors. Um, so what I'm going to be doing in these examples, I'm going to try my best to solve for all the variables, such as like the voltage and the current through each resistor. And also, I'm probably going to throw in some other ways to go about doing it, just so that you can see a little bit of variations of different ways to solve a circuit, because there's not only one way to solve a circuit. There's multiple ways to do it, but ultimately it's up to you to choose the best method for you. But however, the more tools and the more ways you know how to solve a circuit, um, is for the better. It'll make your circuit analysis a whole lot easier and comprehensive. So, um, so for this first example, I'm going to find IT, which is I total, the total resistance, I2, I3, and V1 and V1, V2, and V3. All right, so the first thing you want to do whenever you're approaching a series parallel circuit like this is you want to identify your series resistors, and you want to identify your parallel resistors first. And so if we go about the whole highlighter method, if we do it like that, so we can see that we have three nodes, because we have three colors. So we got a yellow node, a blue node, and a red node. So if we start looking for anything that's in series, we look at, let's look at R1. All right, so R1 comes to this junction point right here, to this node. And at this point, you can tell it's not in series with anything else, because if the current is flowing through R1, now it has options of flowing down and flowing to the right. Remember, in order for two resistors to be in series, they have to have the same current, meaning that the current has to flow. The same current has to flow through the R1 and whatever resistor that it is in series with. So we don't have any series resistors. Well, what about parallel? Remember, parallel resistors share the same two nodes. And so if we look at R2, we can say R2 is, if we compare R2 to R1, we can tell these two are not in parallel, rather, because they don't share the same two nodes. R2 is connected to the blue node and the red node. R1 is connected to the yellow node and the blue node. So these two are not in parallel. Now, what about R3 and R2? Well, R3 and R2 are in parallel, because they are connected by two same nodes, the blue node and the red node. So let's go ahead and combine these two resistors together. And so what I'm after is, I'm just trying to find my R total first. This is what I'm trying to find first. And so whenever you're dealing with series parallel combination resistors, um, you're going to have to redraw the circuit once you start, combining resistors together, to make your analysis a whole lot easier to see. And so if I just redraw the circuit, notice this is going to be my R2, which is in parallel with R3 combination, and this is going to be my R1. So let's calculate R2 in parallel with R3. So I'm going to use the product over sum method. All right, so let me plug that in. All right, so I get 1.66, well, 1.67 kilo ohms. And so this is 1.67 kilo ohms. And so now, once you get to this point right here, you can easily see that R1 is in series with the parallel combination of R2 and R3. And so all we have to do at this point to find R total, let's say R total is equal to R1 plus the parallel combination of R2 and R3. And so R1 is 1 kilo ohm plus the parallel combination, which is 1.67 kilo ohms. And so that equals 2.67 kilo ohms. All right, so that's the first part. So we got that one. And so what else can we find? I total. So I total. Now come over here and start writing. So I total is always equal to your V total or your source voltage divided by your R total. And so do we know our source voltage? Yes, we do, which is 10 volts divided by R total, which we just calculated, which is 2.67 kilo ohms. Right? Let me plug that in. So 10 divided by 2.67 into 3. And so now you have 3.75 milliamps. All right. So that's my I total. And so where is my I total? First of all, so I total is always gonna be right. Is whatever is coming from the source. So I total. And so whenever you look over here on this circuit, well, I total is still gonna be right here. All right, what else we gotta find? We want to find I2 and I3. Hmm. All right, so what we can do here is to find the current in each branch. What we could do is a current divider. And the reason why we can do a current divider is because we know the current that's flowing in this direction. So current gets to this junction right here, and now you get I2 flowing in that direction, then you get I3, which is flowing in that direction. And so how you know you can use a current divider is anytime that you know the total current that's going into a node or a junction point of parallel resistors, you can use a current divider. So basically we're taking this current and we're dividing it up. We're dividing it up based off the resistor value of R2 and R3. And so there's two ways to do a current divider, but I'm going to use this way right here since we already know the total of the parallel combination. All right, so let's see. So I'm solving for I2 first. So I2 is going to equal uh, I total times R2 parallel with R3 divided by R2. Okay, so we have I total that's going into this combination right here, which is we calculated to be 3.75 milliamps. And so we know our parallel combination R2 and R3, which is 1.67 kilo ohms divided by R2, which is 2.5 kilo ohms. All right, and so that equals 2.51 milliamps. All right, and so I3 will be the same type of equation. which R3 is 5 kiloohms. Oh, man. 3.75 e to the minus 3 times 1.67 e to the 3 divided by 5, which is 1.25 milliamps. All right, and so this is one way you can do a current divider. The other way, and this way only works whenever you have two resistors in parallel. Your I total, and you multiply it times your times the opposite resistor that you're trying to find the current through, divided by the sum. And so you get 3.75 milliamps times R3, which is 5 kiloohms, divided by 2.5 kiloohms plus 5 kiloohms. All right, so I'm gonna plug that into the calculator, see if we get the same thing. 3 times so really the denominator is just 7.5 e to the 3. And if you do it this way, you get 2.5 milliamps, which is pretty close to this one. So that checks out. You can do the same thing with I3. You get I total times the opposite resistor that you're trying to find that you're trying to find the current through. So we're trying to find the current through R3. So we're going to take the opposite resistor and put it in the numerator. So this will be R2 divided by R2 plus R3. Milliamps times 5, nope, not 5, 2.5 kiloohms divided by 2.5 kiloohms plus 5 kiloohms. All right. Then we plug that in. And you get 1.25 milliamps. And so that also matches to what we had before. And then another quick little check. Make sure we did this correctly. Is the sum of I2 and I3 should equal the I total. So I total can be called I1, which is the current through R1. But I'm just going to keep it as I total. So if you do a quick look check, I total is equal to I2 plus I3, which is 2.5 milliamps plus 1.25 milliamps, which equals to 3.75 milliamps. And so that checks out. All right. So now let me take a step back and clarify some things. So current divider. So we've been thus far we've been taught that what goes into the numerator of a current divider is the total resistance, R total. However, that was true only when you're dealing with, well, that's true because before we was only dealing with parallel resistors. So the R total was the total resistance of the parallel resistors. In this case, we have a parallel series combination. So if we want to apply a current divider, we only needed to apply it to the parallel resistors, not the total resistors. Okay, like I said before we were only dealing with parallel resistors, so therefore the R total was us just adding the resistors in parallel, and that was our R total. In this case right here, our R total is just going to be R2. Our excuse me, not our R total. The numerator is just going to be the parallel combination of R2 and R3. Hope that makes sense. If it doesn't, feel free to reach out to me. But let's go back up here and let's make sure we got everything. So we got I1, I2, and I3. All right. So what about V1? So V1, we could just do a quick Ohm's law calculations. And so we say V1 is going to equal to R1 times I1. And we all know I1 is equal to I total. So what is R1? 1 kilo ohm. And then our I total was just 3.75 milliamps. Okay, and so that equals pretty much your kilo cancels out your milli. And so that's equals to 3.75 volts. All right, so what about V2? Now V2, we can still do Ohm's law. V2 is going to equal to R2 times I2. So what is R2? R2 is going to be your 5 kilo ohms times I2, which is, what is I2? 2.5 milliamps. So to get here is 12.5 volts. All right. What about V3? So V3 is to R3 times I3. And so our R3 is, oops. All right, let me back up. So this is supposed to be uh, all right, so let me back up. So R2 is 2 point. All right, let me back up. Back up. All right, so let's find V2. So V2 is going to equal R2 times I2. And so R2 is your 2.5 kilo ohms times I2, which is 2.5 milliamps. And so your kilo cancels out your milli, and you're left with what? 6.25 volts. All right, so what about V3? V3 is going to equal your R3 times I3. And so that's 5 kilo ohms times your I3, which is 1.25 milliamps. Your kilo cancels out your milli. And so 5 times 1.25. And you get the same thing. So I went ahead and went through the motions, but you should have noticed that R2 and R3 are in parallel. So obviously, or evidently, that they're going to have the same voltage. So really, we didn't really need to perform this calculation down here for V3. But I went ahead and went through the motions just to show you all that, the calculations work out, how the calculations work out. One alternative way we could have solved this one was using a voltage, Kirchhoff voltage law. And so we already knew that the voltage across R1 was what? Voltage across R1 was 3.75. right? And so if we do a KVL around this inside loop right here, we'll say that, we come over here, 10 volts equals 3.75 volts plus whatever VR2 is. And to solve for VR2, you just solve for it algebraically. Which equals 6.25 volts. And same thing if we would have went around the outside. So we're at 10 volts equals 3.75, which is the voltage drop across R1, and plus VR3. And you get the same thing. All right, so hopefully this example right here was worth it. Keep in mind that you don't have to perform all the little steps that I did. One thing I would recommend you do is to redraw the circuit each time you combine either series or parallel resistors together. So that way you're kind of um, breaking the circuit down one by one, because once you combine, like for example, once we combine R2 and R3, we drew the circuit. Now we can see easily that, okay, that this parallel combination is in series with R1. So hopefully that helps. And I'll see you on the next example. All right, so for example 2, all right, so we take a step back and look and see what we got going on with for example 2. Can't really identify anything right here, but we go towards the end, you can see that, we have R3 and R4. They are connected by the same two nodes. And so therefore, these two are in parallel. So let's go ahead and add those two in parallel first. All right, so R3 parallel R4 equals, all right, put it into the calculator. All right, 8, 3. All right, so that's the parallel combination of R3 and R4 is 1.67 kilo ohms. All right, so once we add these two together in parallel, let's go ahead and redraw the circuit. And so the circuit will look something like this. Which this is R3 in parallel R4, which is 1.67 kilo ohms. And then this is R2, which is 1.5 kilo ohms. And this is your R1, is 1.1 kilo ohm. All right, so from here, we can see that this parallel combination of R3 and R4 is in series with R2. So we can just add those two together. The R2 plus R3 parallel R4 equals 1.5 plus 1.67 kilo ohms. And so that equals 3.17 kilo ohms. All right, so now once we do that, let's go ahead and redraw the circuit. So this resistor right here, this is going to be R2 plus R3 in parallel with R4, which equals to 3.17 kilo ohms. All right, and so now we can see that R1 is in parallel with this series parallel combination that's to the right of it. All right, so we just add them up in parallel. So we have, so really this is going to be our total. Our total is going to equal 1 over R1 plus 1 over the R2 plus R3 parallel R4, which equals 1 over R1 with 1 kilo ohms plus 1 over 0.17. All right, and so we plug that into the calculator. Let's do that right now. All right, so you get 760 ohms, 0.19. All right, so that's our total. And if you look and you ask yourself, does this make sense for our total to be 760.19 ohms? Well, it kind of does. It does, because the total resistance of a parallel circuit, which right now, this is a parallel circuit right here. This is a parallel circuit that we reduce it down to. The total resistance is going to be less than your smallest resistor. In this case, 1 kilo ohm is our smallest resistor in this reduced circuit that we just reduced it to. And so 760 is smaller than 1 kilo ohm. So that makes sense. All right, so that's our R total. All right, what else we gotta find? We gotta find I total, which we just use Ohm's law for I total. I total equals, keep saying V, E over R total, which is 10 volts divided by 760.19 ohms. So 10 divided by 760.19. 10 divided by 760.19 equals 13.15 milliamps. All right, so we found R total. So let's start plugging R total in here. I mean, we just found I totals. So I total right here, which is 13.15 milliamps. All right, and so it comes to this point right here. All right, and so some of it goes down, which is I1, and some of it goes to this way, which is I2. All right, so how do you know how much is going down? Well, at this point, we can do a Ohm's law because we know the voltage across R1, which is because R1 is in parallel with the source. So therefore we can do a voltage. I'm sorry, we can do Ohm's law, which says I1 equals VR1 divided by R1 equals 10 volts divided by 1 kilo ohm, which equals to 10 milliamps. And so we can come back up here and we can plug in 10 milliamps right here. And so knowing that, I2 is going to equal the total current minus I1. I2 is going to equal I total minus I1 was 13.15 milliamps minus 10 milliamps, which equals 3.15 milliamps. Right. All right, so now that we know the current is flowing in this direction, how can we find out the current that's going through our R3 and R4? Well, we can do a current divider. Yeah, we definitely can do a current divider, similar to what we did in the last example. But let's try to see if we can do it a different way. Um, I'm going to use Kirchhoff's voltage law. But in order for me to do that, I need to figure out what is VR2. VR2 is equal to 3 point I2 times R2, which equals to 3.1 milliamps times R2, which is 1.5 kilo ohms. So that equals to 3.15, 4.73 volts. So this is 4.73 volts. And so therefore, if we do a KVL around this loop right here, we can say your 10 volts equals VR2 plus VR3. And so that 10 volts equals, we already found the VR2, which is 4.73 volts for VR3. We just solve for algebraically, so VR3 is equal to 10 volts minus 4.73 volts, which equals 10 minus 4.73, 5.27 volts. And so therefore, if we solve for this voltage, which is 5.27 volts, 5.27 volts, then R3 and R4 in parallel with each other. So therefore, we know that voltage as well. So VR4 equals VR3, which equals 5.27 volts. Therefore, we can solve for the currents through each of those branches by using Ohm's law, because we know the voltage, we know the resistance, so we can just use Ohm's law to solve for the current. So I3 is equal to VR3 divided by R3, which equals to 5.27 volts divided by R3, which is, what is R3? 2.5. So we get 2.11 milliamps. And we could use Ohm's law again to solve for I4, but I'm going to use Kirchhoff current law. So let's say I2 minus I3. And so you get 3.15 milliamps minus the 2.11 milliamps. And so you get 1.04 milliamps. All right, and you ask yourself, does that make sense for I4 to be smaller than I3? Well, in order for that to happen, R3 has to be smaller than R4. And is that the case? It is the case because current mostly follows the path of the least resistance. So what that means is when I2 gets to this junction right here, majority of the current is going to follow the path of the least resistance. And in this case, the least resistance is the 2.5 kilo ohms. So that's another quick little check that you can make to see whether or not if your calculations actually make sense. So that's it for example 2. I'll see you on the next one. All right, so for example 3, we do the same thing, take a step back and we try to see if we can combine anything, either a simple parallel combination or a series combination. And so right now, the only one that I can see that's pretty straightforward would be these two resistors right here that are obviously in series because they share this node right here. And you can see and you can tell that once current flows down in this direction, is no other way for it to flow other than through R2. Now, if you had another resistor right here that was doing something like this, now R1 or R2 would not be in series anymore. But because it's not there, it is. So Let's go ahead and do that first. Let's add R1 and R2 in series and redraw a circuit. So this is going to be R1 plus R2 equals 5 kilo ohms plus 3 kilo ohms, which equals 8 kilo ohms. And then you have your 1 kilo ohm right there. All right, so the next thing we can do is we can see that the series combination of R1 and R2 is in parallel with R3. And so therefore we can add those two together in parallel. And we'll have something like this. All right, and so let's go and add those in parallel. So this will be R2, R1 plus R2, which is in parallel with R3. And so R total is going to equal R1 plus R2 is in parallel with R3. And so that equals 1 over R1 plus R2 plus 1 over R3, which is 1 kilo ohm. R3. And so let's see. All right, I'm plugging into the calculator and see what I get. So I get 88.89 ohms. And so ask yourself, does that make sense? It does, because if you look at this combination right here, this parallel combination, it is less than the smallest resistor. All right, so if we're trying to find the current through R1 and R2, so we already know it's supposed to be the same, right? So it doesn't matter if we try to analyze it using this circuit right here or this one, because the only thing that's different is that these two resistors are added together. But we know that this current is going to be the same. So regardless if you have them separated or combined, it's going to have the same current regardless. So we can actually use this circuit right here to find the current that's flowing through R1 and R2. And so the easiest way to do that is to use Ohm's law, because we know the voltage across this series combination of R1, R2 because it's in parallel with the source. So let's do that. So we'll call this as I1, which equals I2, which equals R1 plus R2 which equals V to R1 plus R2 divided by R1 plus R2. And the voltages across that that series combination is 24 volts divided by 8 kilo ohms. All right, so which equals to 3 milliamps. So we just solve for this one, solve for that one. All right, so what about R3? Well, R3 is the same principle. R3 is in parallel with the source as well. So it's gonna have the same voltage. So we can use the same formula, Ohm's law. So I3 is going to equal the V R3 divided by R3, which equals 24 volts divided by R3, which is 1 kilo ohms, which equals to 24 milliamps. So we got this one. Now, and we solve for R total. What about I total? Now we didn't use our V, the source voltage divided by R total, like we did before. I want to solve this one going about it a different way. And so we know that current that's flowing in the direction of R1, R2, and in the direction of R3. You add those two up together, you should get I total. And so let's do just that. And that's Kirchhoff's current law. So I total is equal to we call this I1, 1 and 2 plus I3. And so that's going to equal I1 and 2, which is 3 milliamps, plus I3 is 24 milliamps. Which equals to 27 milliamps. And if we wanted to, we can go ahead and solve it like we usually do. So I total is equal to E over R total, which is 24 volts divided by R total equals what? 888.5 888.89. 888.89 ohms. So let me divide that and see what we get. So 24 divided by 888.89. And you get just that 27 milliamps. All right, what else we need to find? We need to find VR1, VR2, and VR3. So we can go about this one. I'm trying to think. Let's do a voltage divider to find the voltage across VR1 and VR2. All right, so VR1 is going to equal. So first of all, what is the total voltage that's across this series combination? So the voltage across this series combination is the 24 volts. And so therefore we have E times, let's see, R1 over R1 plus R2. And so you get 24 volts times R1, which is 5 and 3. Divided by 5 plus 3 kilo ohms. All right, and so if we plug it into the calculator, 24 times 5 equals 3 divided by 8 kilo ohms. You get 15 volts. And VR2 will equal E times R2 divided by R1 plus R2. It's 24 volts times here 3 kilo ohms over 5 kilo ohm plus 3 kilo ohms. I'm plug that into the calculator. Equals 9 volts. Now keep in mind, I could have used Kirchhoff voltage law and solved for VR2 algebraically. That's another method. I could have used Ohm's law because we know the current that's flowing through each one of these resistors, and we know the resistor values. So you just simply do a quick Ohm's law. You could have solved for it that way. And I encourage you to do so on your own to see if you come up with the same answers. Now, the last one we have to find is VR3 And so VR3 should be a gimme because we already know that anything that's in parallel has the same voltage. And so VR3, the resistor 3 is in parallel not only with R1 and R2, but it's also in parallel with the source, in which, in this case, the source is dictating the voltage. So VR3 is going to equal 24 volts. So that's it for example 3. And I'll see you on the next one. All right, so this is going to be the last example, and I'm not gonna solve it entirely. Well, I may. Uh, but let's take a look at this one. This one is kind of unique because it has this line right here that doesn't have a resistor on it. And so basically what this is representing is a short. And what a short does is essentially it shorts out everything that is in parallel to it. So think of it this way. So once current flows in this direction, it has a choice of going here, now here, or here. Well, what did we say before? Current mostly follows in the direction of the least resistance. And right now, I mean, this is looking like it doesn't have any resistance. So majority, if not all, of the current is going to, it's not even going to flow in the direction of R3 and R4. It's going to keep on going. So it's almost as if R3 and R4 are not even there. And in fact, you can kind of look at it that way. But if you model this in real life, there is some, and I mean some, very little that's going to flow in the direction of R3 and R4. But for the sake of this class, anytime you see a short, we're going to assume that zero current is flowing through the parallel resistors that are in parallel with a short. Oh, all right. So really what we can do is we can, redraw this circuit. I actually redraw it down here. We can redraw this circuit since we know that. And so essentially what the circuit is going to look like is this right here. That's your R1, which is 1 kilo ohm. R2, which is 1.5 kilo ohm. And this is just short. So these guys are not even here because it's in parallel with this short right here. And it doesn't matter if the short is behind it The short could have very well been right here, or it could have been right here in the middle. But the key thing to remember is a short shorts out any resistors or any elements that are in parallel with it. So all you really have to do is just replace it with a straight line or a short, just like we did right here. So we just took R3 and R4 and just replaced it with a straight line. And so if we're looking for R total is going to be, well, let's look at this circle right here first. All right, so R1 and R2, are they in series or parallel? Well, they're sharing the same two nodes, which we can see that from our highlighted method. So therefore they're in parallel. So we just, once we combine those two together, we'll just have one resistor, which will be R1 in parallel with R2. And so which equals R total. R total is going to equal your 1 kilo ohm times 1.5 kilo ohm divided by 1 kilo ohm plus 1.5 kilo ohms. And if I throw that into the calculator, equals 600 ohms. And so from here we can just start doing what we've been doing in other examples. If we wanted to find our total, or find I total is going to equal E over R total, which is going to be your 10 volts divided by 600 ohms. Which is 16.67 milliamps. So really, I mean, at this point, you can kind of really forget about this circuit right here. You can just kind of key in and focus on this one. So this is your I total right here. And so from here, you can do you want to find a current in each branch, do a current divider, or you can do Ohm's law. We know the voltage across R1 and R2 are going to equal to 10 volts because they're all in parallel. So at this point, it's kind of up to you how you want to solve it. But I'll just pick one method. I'll do Ohm's law. So we say I1 is equal to VR1 divided by R1, which equals 10 volts divided by 1 kilo ohm. Be 10 milliamps. I2 VR2 divided by R2 equals to 10 volts divided by 1.5 kilo ohms, which is going to be 6.67 0.67 milliamps. That's pretty much all there is to it. The main thing about this one is I wanted you to see the effects of a short right here. This is a short. And basically all it does is that it shorts out, or you can say it even eliminates anything that's in parallel with it. So in this case, this short right here eliminated R4 and R3, and they've been replaced with just a simple short right here. All right, so that's it for that example. So hopefully these examples are beneficial to your understanding of this topic. But if you have any questions, feel free to reach out to me.